Welcome to the e-Pathshala lecture series on computer science for postgraduate students. We will be discussing the graphics and visualization. Our subject is computer graphics and visualization. This is our third session in the series. As we discussed in the previous sessions, in the last two sessions, some of the very basics and fundamentals in the first session, and followed by that in the second session we talked about DDA line drawing procedure. It's a simplicity, it's the most simplest algorithm and its drawbacks. So, in this session we will talk about the Bresenhams line drawing procedure, which is a more efficient procedure than the DDA procedure, and which whose strength is that it does not have floating point calculations that are required in the case of DDA procedure. So, there is no rounding off required, there is no floating point calculation required, and so it is more efficient and it is also more accurate than the DDA procedure. So, let us discuss in this session the Bresenhams line drawing procedure. So, Bresenham happened to be one of the most popular scientists and who has given some of the very useful algorithms like Bresenhams line drawing procedure, and Bresenhams circle drawing procedure was also very popular till late 90s, and later another type of procedure, there is a different type of procedures were developed and more advanced procedures were developed for circle drawing. So, let us discuss today about the Bresenhams line drawing procedure. So, to start with, how Bresenham is more efficient is that it avoids floating point calculations, and so no rounding off and no other errors, and it is also more accurate. So, imagine you are given a line whose slope is like this, say for example, m is less than 1. So, if you recollect the discussion on DDA line drawing procedure, we talked about various line types. So, lines are inclined towards x axis or towards y axis, or maybe the line slopes are equal to 1, sometimes dy is equal to dx. So, whatever be the line types, so depending on how the line is inclined, we are going to sample the line either along x axis or along y axis. So, imagine a line which is inclined along x axis. So, we follow the same analogy here or the same discussion, like we are going to sample the line along x axis at unit intervals if the line is more inclined towards x axis. Now, let us assume that we have point on the line that is already plotted, that means we know a point on the line whose coordinates are known to us. Let us say the coordinates are x k and y k, and for which a pixel is plotted on the line. So, let us see how Bresenham's procedure tackles this problem of finding more accurate pixels along the line path. Here our initial assumptions start with assuming that the line has slope less than 1, and we are going to sample the line along x axis at unit intervals. So, the same arguments are valid, like the next x value, because for the sampling along x axis is actually x k plus 1. So, the next, to indicate next x value, we use a notation x k plus 1, and where k plus 1 all in the suffix, whereas this indicates that x k plus 1 by the side indicates that x k is a previous value and we are adding 1 to it. So, always whenever we use the word next, we use a notation k plus 1 in the suffix. Okay. So, start with a known point on the line, say x k comma y k, that is which is a known computed point on the line. So, our aim is to compute the next unknown point on the line. Let us indicate that as x k plus 1 comma y k plus 1. So, how do we compute the unknown point on the line? The next unknown point is by a variable which we call it as decision parameter. So, for every next computation or for computing every next value, we will be using this value or the variable called decision parameter, and whose value will be helping us to compute the next x value and the next y value. So, let us see how do we compute the next x value and the next y value based on the decision parameter. So, what is this decision parameter? We will understand that at depth here. see this slide here. For the next x position, that is, imagine you have got a line which is inclined towards x axis, which is more inclined with x axis or more towards x axis. So, we have a known point on the line which is already plotted, say x k y k. Now, because the line is more inclined towards x axis, we are going to sample the line along x axis at unit intervals. That is the best possible sampling frequency. So, for the next x value on the x axis, so we are indicating that with the notation x k plus 1, because as we know that the next x value is 1 higher than the previous x value. So, how do we compute the corresponding y value? So, the y coordinate for this x coordinate, that for the corresponding y coordinate can be either y k plus 1 or y k. So, as you see here, the possible pixels that we can plot on the monitor is y k or y k plus 1, because as we know that all monitor pixels are integer positions. So, even if we compute using some point slope form that y value is somewhere here between the two integer positions, we cannot actually plot this point. So, this is what is called the theoretical position. So, here y indicates the theoretical y coordinate which cannot be plotted on the monitor. So, we have to choose either y k plus 1, the upper pixel, or the lower pixel. Now, how do we decide which of the two pixels is to be chosen, so that we can better approximate the theoretical line path? So, here you have to understand one important point: whatever pixels that we are computing along the line path are an approximation to the true line path. An approximation means we are trying to find the best possible approximation. So, always we get an approximated line, we never get the true line. So, that is understood. So, we always get an approximated line. So, how to choose whether y k or y k plus 1 is the next possible position? So, for this, here we will be computing the vertical distance here between y and y k, and the vertical distance between y and y k plus 1, and see whichever position is closer to the theoretical y value, that is y. If this is closer, y k plus 1 position is closer, we will be plotting that, or if this theoretical position is close to the lower pixel y k, then we will be plotting this. So, in the diagram that is shown, the upper pixel is more closer, as if you compute the distance d upper, we call this d upper. D upper is the distance between y and y k plus 1, d lower is the distance between y and y k. Whichever distance is smaller, so we will be choosing the corresponding pixel. So, that is the theory behind the Bresenhams, that is the whole idea, that is the principle of Bresenham's line drawing procedure. So, for computing every next position on the line, we will be checking whether the true theoretical position or the true position on the line is close to either of the pixels. So, to whichever pixel position the true theoretical line true theoretical position is closer, we will be choosing that position. So, it will be clearer to you when we solve a problem, and we are going to do a derivation on this and how to compute the decision parameter and so on. So, you will be having more clear idea when we solve a problem at the end. So, as you see here, the next position to be plotted is x k plus 1 comma y k. So, the y coordinate is either y k or y k plus 1. So, how do we decide whether it is y k or y k plus 1? The x coordinate is the same. The y coordinate is chosen based on the decision parameter. So, let us come to check how this decision parameter is actually computed, and in the derivation we will be doing this. So, a decision parameter is basically, it is denoted as p suffix k, helps us decide which of the pixels to be chosen. Okay. So, and whichever pixel is close to the theoretical position, we will be choosing that pixel. Okay. So, the next x, so next here is always indicated with k plus 1 in the suffix, and because we are confident that the line is more inclined towards x axis, we are going to sample the line along x axis at unit intervals. So, the next x is nothing but x k plus 1. while the next y is yk plus 1, which is yk or yk plus 1 depending on the decision parameter. So, let us see how we do the derivation, or how do we find equations for the decision parameter, and what is the decision parameter. Let us start the derivation with y is equal to mx plus c, that is the slope point form equation for a line. Here this is the theoretical y value, and in the place of x it is xk plus 1. So, xk plus 1 is the current x position for which we are computing the y position. So, that is why the k plus 1 is all in the suffix, and we know very well that k plus 1 xk plus 1 is nothing but xk plus 1. And d upper is, if you look at this diagram shown here, d upper is the difference between y and yk plus 1. Okay. So, which is yk plus 1 minus y, because the difference is to be positive. So, d lower is the difference between the y and the yk. So, that is what is shown here, y minus yk, and you can expand d upper further like this, yk plus 1 minus y is shown here above. So, for y you replace this y, or substitute for y this equation like m into xk plus 1 plus c. So, yk plus 1 minus m into xk plus 1 minus c. So, because it is y yk plus 1 minus y. So, these two terms become minus, and d lower similarly is y minus yk. For y substitute this relation here above, which is m into xk plus 1 plus c. So, m into xk plus 1 plus c minus yk, and we are now taking the difference then to compare the d lower and the d upper. So, one important decision, or one important step that we are doing here is then to compare the magnitudes of d lower and d upper. So, if d lower is greater than d upper, so what is that we do is we will be choosing the upper pixel. If d lower is less than d upper, we will be choosing the lower pixel. So, if d lower is equal to d upper, we can be choosy about, we can choose either of the positions. So, you can follow one convention throughout, you can choose always either the upper pixel or always either the lower pixel, and so on. So, if we come to the difference here, we will not be actually comparing d lower and d upper, rather we will be taking the difference of these two magnitudes and we will be finding the sign or checking the sign of this difference operation. That is, if d lower minus d upper greater than 0, that does mean that d lower greater than d upper. So, d lower greater than d upper means we will be choosing the upper pixel. So, similarly, if d lower minus d upper less than 0, that means the difference operation is less than 0, it is negative, that means d lower less than d upper, choose the lower pixel. So, as we got the equations for d lower and d upper already here, take the difference of these two, d lower minus d upper. So, which gives us an expression like this, 2 times m xk plus 1 minus 2 yk plus 2 c minus 1. You can sit and you can follow when you start doing for yourself, you will be able to resolve these equations, you will be able to solve these expressions more easily when you take a pen and a paper and note it down and keep resolving these equations. So, one important step. So, here Bresenham was very clever enough in taking one important decision, that is how to avoid floating point calculations, or how to avoid completely the floating point values. So, Bresenham was clever enough here at this exact step to substitute for m the delta y by delta x, because m is the culprit here, that is m is a division. So, whenever m has got whenever there is a division in an expression or in an equation, it causes floating point values. So, divisions are to be avoided. So, Bresenham was clever enough in avoiding this division by substituting for m delta y by delta x and taking this delta x on this side, cross multiplying delta x on either side, and so that the division is altogether avoided. So, if you look at this step, this delta x is multiplied onto the left with delta x into d lower minus d upper, and is equal to you multiply delta y with the rest of the with the term 2m into x k plus, that is 2 x k plus 1 into delta y minus this delta x is to be multiplied on this side also, delta x is to be multiplied on either side. Okay. So, 2 delta y x k plus 1 minus 2 delta x into y k plus delta x into 2 c minus 1. So, this term is what you should remember, and Bresenham has actually replaced this term d lower minus d upper into delta x as the decision parameter p k. Why it is called the decision parameter is because the difference of the operation d lower and d upper is going to tell us whether the lower pixel is to be chosen or the upper pixel is to be chosen. That is, if d lower minus d upper is less than 0, that is sign bit. So, check the sign bit of this difference operation. If the sign bit is set, that means the lower pixel minus d lower minus d upper is less than 0, that means d lower is the more distance is smaller. So, it is closer to the lower pixel. Okay. So, the lower pixel is to be chosen. So, the sign bit of this operation is always to be verified. So, the p k is now called the decision parameter, and p k is nothing but the difference operation d lower minus d upper multiplied with delta x. Now, you can ask like say why should we go with delta x, there is some other additional term delta x, what should we do with it? For lines whose slopes are inclined, whose slopes are positive, you can actually you will get delta x to be positive. So, positive multiplying with some positive or negative is not going to affect the sign of the difference operation. So, delta x is not going to affect the sign of the difference operation d lower minus d upper. So, we can safely ignore del x, and that is why we call this parameter as p k a decision parameter. So, it is just enough that you take the sign of the difference operation. Okay. So, here the left part of the equation has been replaced with p k, which is nothing but del x into d lower minus d upper. It is equal to the right side part is left as it is, and we know that because we are sampling the line along x axis at unit intervals, x k plus 1 is equal to x k plus 1. So, but y is to be decided whether it is y k plus 1 or y k depending on the sign of p k, okay, depending on the sign of p k. So, substitute for x k plus 1 the next x value as x k plus 1. So, this equation reduces to 2 del y x k minus 2 del x y k plus 2 del y plus del x into 2 c minus 1. So, that is how this equation reduces to, and if you consider the rightmost part of the equation here, del x into 2 c minus 1, del x is a constant for a given set of endpoints, del y and del x are constants, c is a constant for a line, this is an intercept, c is the intercept, y intercept. So, this whole part is a constant which can be conveniently replaced with a constant say b. So, p k is nothing but 2 del y x k minus 2 del x y k plus b. Because program has to be more efficient and we want always equations that depend on the previous equations for faster calculations. So, we require recursive equations. So, that is we always want decisions based on the previous calculation. So, recursive equations will be much more faster and simpler. So, that is why what we are doing, we are actually taking the next decision parameter, c in the suffix k plus 1, k plus 1 in the suffix indicates that it is the next decision parameter, and wherever there is k we are replacing that with k plus 1 in the previous equation. In the take the previous equation, wherever there is k replace that with k plus 1. So, which is 2 del y x k plus 1 minus 2 del x y k plus 1 plus b. Now, take the difference of these two decision parameters p k plus 1 minus p k, which is equal to 2 del y x k plus 1 minus x k minus 2 del x y k plus 1 minus y k. So, you can sit and take these, and while you write it down you will have more clarity and you will not miss the discussion and the derivation further. So, all the steps are given in detail here. So, you can follow that carefully. So, the next decision parameter is actually, so take this pk plus 1 is minus pk is equal to what is the previous equation, take this pk on to the right. So, what do you get is this. So, the next decision parameter is dependent on the previous decision parameter plus some additional terms. So, the next decision parameter is given by pk plus 2 del y. If you notice this difference here, xk plus 1 minus xk is actually xk plus 1 is the next x value, which is 1 higher than the previous x value. So, xk plus 1 is nothing but xk plus 1. These two terms xk and xk get cancelled and you are left out with 1 here. So, pk plus 2 del y minus 2 del x yk plus 1 minus yk, this term remains as it is. Now, our aim is to check or verify or compute or derive what this yk plus 1 assumes, or whether it is yk or yk plus 1. So, this is the next y value. So, the next y value will be decided based on the sign of pk. Okay. So, the sign of pk is to be checked. Now, let us come to case 1. Case 1 says that let us assume if pk is less than or equal to 0. Pk here is what? D lower minus d upper. D lower minus d upper less than 0, that means d lower less than d upper. D lower less than d upper means the lower pixel is more close to the theoretical line path. So, we will be choosing for the next y yk. Okay, if you remember the first graph, yk and yk plus 1 are to be decided, or which of these two is decided based on the sign of the difference of d lower and d upper. So, if d lower minus d upper less than 0, this pixel is more close. So, we say that yk is the pixel position, y coordinate to be chosen for the next y. So, that is what we have done here. So, case 1, if pk is less than 0, the lower pixel, that is for y, you will be choosing the next y, you will be choosing yk, that is the next y is actually yk. So, when the next y is yk, now compute the equation for the next decision parameter, replace this yk plus 1 with yk. So, yk get cancelled and this whole term becomes 0 and you are left out with the next decision parameter is equal to pk plus 2 delta y. So, similarly, you do this for the pk greater than 0 case. In the previous case, we took the case less than or equal to 0. Now, pk greater than 0, pk here means d lower minus d upper, d lower minus d upper greater than 0, that means d lower greater than d upper, that means choose the upper pixel for the y. So, this upper pixel is the yk plus 1 position, and the next pixel to be plotted is xk plus 1 comma yk plus 1. And as you see here, the next y value is nothing but previous y value plus 1, as we replace that with. And if you compute the next decision parameter, replace yk plus 1 in this equation here, replace yk plus 1 with yk plus 1, and you are left out with this equation, that is, you can, when you solve that, what you get is pk plus 1 is equal to pk plus 2 delta y minus 2 delta x. So, finally, we got the two cases, and quickly if we summarize this, that is, if we look at the decision parameters, we are using the notation k in the suffix. So, that means unless we are also using recursive equations. So, every next decision parameter is dependent on the previous decision parameter. So, we have to start with some known initial parameter, isn't it. So, that means we have to start with k is equal to 0. Unless we know the initial decision parameter, we cannot compute the next decision parameter and so on. So, how do we go with p naught? How do we calculate p naught? So, in the equation for pk is equal to 2 del y xk plus 1 minus 2 del x yk plus 1, or you can take this equation 2 del y xk minus 2 del x into yk plus 2 del y plus del x into 2c minus 1, replace the subscript k with 0. So, that is how we replace subscript with 0. So, that is p 0 is equal to 2 del y x naught minus 2 del x y naught plus 2 del y plus del x into 2c minus 1. So, that is what is mentioned here in this slide, k with 0, replace k with 0 and compute c as shown. If you replace k with 0, you have this equation as 2 del y x naught minus 2 del x y naught plus 2 del y plus del x into 2c minus 1, and the c is colored in red to indicate that this is the odd man out in this entire equation. If you see, there are delta x's, delta y's, x k's, x, y and so on, except one term which is c, which is an odd man out, and we have to replace c with some other term. Let us see how to compute that c. So, we know that from the slope intercept form we have this equation y is equal to mx plus c, and any point on the line should satisfy this equation y is equal to mx plus c. So, as we know that x naught y naught is the first known point on the line, you can substitute here for y naught, for x naught, and we can write this equation. Now, c is equal to m is replaced with delta y by delta x. So, c is nothing but y naught minus del y by del x naught, and in the equation here replace c with the colored in red, c is colored in red, replace c with this expression y naught minus del y by del x naught. So, when you sit and solve it, what you would get is, if you solve with these steps, it would reduce to a term, an expression 2 del y minus del x. So, P naught is a simple expression with 2 del y minus del x. So, the initial decision parameter is computed and the next decision parameters are computed based on the previous decision parameters. And if the point on the theoretical line is equidistant from either of the possible pixel locations, then either of the pixels could be plotted. So, whether if pk is less than 0, you are choosing the lower pixel, if pk is greater than 0, you are choosing the upper pixel, but if pk is equal to 0, you can choose either of the pixels. As I said earlier, you can you can follow a convention throughout, that is, choose always the upper pixel or choose always the lower pixel, it is up to you, but follow a convention throughout. Okay. So, the steps can be summarized for m less than 1 case like this. So, we are choosing a case here, m is less than or equal to 1, and we are going to sample the line along x axis at unit intervals, and the first step is to input the two endpoints. For the procedure is summarized here, you can look at this carefully. The input is the two endpoints of the line. The next step, immediate next step, is to compute P naught using the relation 2 del y minus del x, and check the cases depending on the sign of P naught. Now, if you are getting P naught to be negative or positive or maybe equal to 0, so based on that we will be choosing what is the next y value. Okay. Continue with the next decision parameters till the end of the line is reached. So, that is how it is as simple. We can use the equations in the previous cases that were mentioned, case 1 and case 2. Okay. So, that is how we do the derivation, and now the question is what will happen to the relations here when the slopes are greater than 1, positive, negative. So, we have seen an example or a derivation assuming that the slopes of the lines are less than 1, that means the lines are more inclined towards x axis. So, what will happen to the derivation, to the equations, if m is greater than 1 or m is negative and so on. So, let us summarize the steps for m less than 1 first, and then we will move to the other cases. So, case 1, when m is less than 1, P naught is 2 del y minus del x, and if pk is less than or equal to 0, that means the lower pixel is more close to the theoretical position. So, we will be choosing for the next y, yk. So, the next y is yk, and pk plus 1 is pk plus 2 del y. For the second case, when pk is greater than 0, the upper pixel is to be chosen, and the next y is previous y plus 1, and the next decision parameter is pk plus 2 del y minus 2 del x. And if m is greater than 1, so without doing any derivation we can come to one important conclusion, because if m is less than 1, the line is more inclined towards y axis, and we are going to sample the line along y axis at unit intervals, and we will be following the same set of procedures and equations. So, if you start doing the derivation for this case, you will end up with equation for P naught to be 2 del x minus del y, that is exactly a reversal of the x's and y's. So, x and y get interchanged. So, wherever there is x, that will be replaced with y, wherever there is y, that will be replaced with x. So, P naught is equal to 2 del x minus del y. If p k less than 0, for this case m greater than 1 case, if p k is less than or equal to 0, y will be incremented by 1 unit. So, we do not have to worry about y always gets incremented by 1 unit because m is greater than 1, while x is to be decided whether it is x k or x k plus 1. Because the sign is less than or equal to 0, that means it indicates that the left pixel is more close to the theoretical position. So, that is x k. We chose earlier the lower and the upper to indicate the y's, but here for the x values we have to compute because the y's are incremented by 1 unit. We use the term left and right to indicate x k and x k plus 1. Okay. So, the derivation goes similarly, and we end up with equations where the x's and y's just get interchanged. So, all the equations are summarized here for various cases, positive, negative and so on and so forth. One important thing that all of you should remember is whenever you have to compute for the negative case, when m is negative, do not substitute for del x and del y's then the corresponding negative values, take only the magnitudes. So, our aim is not to actually take the signs for del y and del x, they are no way to be taken. You can take only the magnitudes of del y and del x, and for the negative case particularly you have to be more careful because you will get all negative values or all positive values, that is a wrong sign. So, one important thing observation about Bresenhams is the sign actually flips between positive, negative and 0. So, it actually fluctuates between positive values, negative values and the 0 value. So, it fluctuates. So, it will not be either too positive, always positive, or it will not be always negative. Yeah, as you see in the slide here, for all possible line types everything is summarized in the slide. So, if m is less than 1 and m is positive, what should you do? What set of equations you should use? If m is greater than 1 and m is positive, what set of equations you should use for the p k less than 0 and p k greater than 0 case? And the same thing is summarized for the negative case, that is if m is less than 1 and m is negative, that means the line is inclined towards x axis, but while x increases and y decreases. So, that is what is a negative slope line. So, here the set of equations are given here, you can refer to these equations, and as you notice here there is the modulus, the delta y's and delta x's you should not be using, even if slope is negative you should not be actually going for negative values, you should be using only the magnitudes, you should be taking only the magnitudes. For m greater than 1 and mod m greater than 1 and m negative, we have the other set of equations shown here. So, you can sit and make a note of all these, and so that for whatever be the line type you should be able to choose the right set of equations. In this session what we have learned, let me summarize. Let us just take a recap, and we have started with how Bresenham's line drawing procedure solves the problem of, that is a more efficient, more better lines can be drawn with Bresenham's procedure, is because Bresenham has cleverly avoided floating point calculations by replacing m with del y by m with del y by del x, and later taking away the division onto the other side and doing some cross multiplication. And the next thing is where Bresenham was clever enough was to use recursive equations, and then using a concept called decision parameters. So, we get more efficient lines, and the errors or issues of rounding off errors or nothing like that exists in this case, and that is what we have learnt in this session. So, we have outlined the Bresenham's line drawing procedure for all possible line types, and also noted the advantage of Bresenham's procedure over the DDA procedure. Thank you.